Am I audible? Uh, you can reply in the chat or someone can unmute. Am I audible? Am I audible? Okay, so let's begin. Hello and welcome to week 3 of these problem solving sessions for the NPTEL course Advanced Power Electronics and Control, which is being taught by Professor Vik Bhattacharya. My name is Soleh Khan and I'm a PhD scholar at IIT Delhi. I will be conducting these problem solving sessions on Mondays. So I will be summarizing the contents of the this week's lectures, and I will solve some sample problems related to those lectures. And since the assignment problems solutions have already been given in the uh, course platform, so I will not be discussing those here. So I will start with the summary of the week 3 lectures. So in this week, the single phase converters, the rectifiers were concluded, and three-phase converters as well as multi-phase converters, these subjects were taught along with the effect of source inductance. Another topic was started about the PDM rectifiers, but we will take that in the next week when we can go into that topic deeply. So uh, we can begin with the types of rectifiers. So rectifiers can be using a single phase supply or a three-phase supply. And in each of these cases, the rectifiers can be uncontrolled. That means they use diode. Half controlled. That means they use a combination of diodes and thyristors, and fully controlled, which use SCRs only. And in the single phase version, we can have uh, half wave rectifiers, uh, and in both single phase and three phase, we can have half wave as well as full wave rectifiers. In full wave, we have two options: split phase supply or a full bridge. And this split phase supply is only the case for single phase converters. And we'll see the circuits of all these types of rectifiers. So first of all, start with the single phase half wave rectifiers. So on the left is the uncontrolled rectifier using a diode, and on the right is a controlled one using a thyristor. So these are half wave because uh, they only convert the positive half cycle of the uh, supply voltage. And then we can have full wave rectifiers. This is the example of split phase supply, which uses a transformer with a center tap secondary side. So the secondary has basically the winding has been tapped in the center, so we get two voltages on the output, and then we use two diodes or two thyristors depending on whether we want uncontrolled or controlled supply. But since these center tap transformers are not very common and they are costly and bulky, these types of circuits are not usually used. So what we go for is the bridge rectifiers. So here you can see three types of circuits. On the leftmost is the uncontrolled full wave bridge, and this is using diodes only. In the middle is a semi-controlled or a half-controlled. This is called a semi-converter. It uses two thyristors and two diodes. So here I've shown two thyristors on the top and two diodes at the bottom, and it can have other configurations also. So in one leg you can have thyristors, in another you can have diodes, or and so on. So different combinations are possible. This is one combination. And on the rightmost we have the fully controlled or a full converter, it's also called, using four thyristors. And in all these cases, both the positive as well as the negative half cycle of the input voltage supply, they are uh, converted into DC. So these are full wave rectifiers. So these were the examples of single phase. Now we come to three phase. So as you know, three phase power is a constant power compared to the pulsating power in a single phase system, as well as we can get the same power with using smaller conductor sizes in three-phase systems. That is why three-phase systems are preferred for high power applications. So on the left, we again have, so this again for half wave, we have two options. We can have the uncontrolled one or a controlled half wave system with diodes and SCRs respectively. So here we don't have any split phase converters, or if we do, I have not seen any split phase converters. They must be very uncommon. What we go for is the full wave bridge converters. And again, I've shown three examples. On the left is the fully uncontrolled using 6 diodes, and on the rightmost is the fully controlled with using 6 thyristors. And in the middle is a half controlled or a semi converter, which can have 3 thyristors and 3 diodes in different combinations. So these are the circuits of all the different types of rectifiers that were taught in this week. And so another converter that was taught was a dual converter, which is just this converter, another of these converter connected on the other side, which allows for a negative current, as so therefore we can have 4-quadrant operation. But the basic circuits are only based on these converters that I've shown. Now, apart from the half-wave rectifiers, all the other circuits that we have seen, they have multiple SCRs or diodes connected to a single point. For example, here I've shown a single-phase full bridge diode circuit, and as you can see in the P point, diode number 1 and 3 are connected to the same point. Similarly, at the N point, diode number 2 and 4 are connected at the same point. So the question is, how do we determine which diode will conduct? So that if we understand that, then we can be able to solve or understand how these different circuits work. So I can redraw this circuit as I've shown here on the right. So if you see the diodes 1 and 3, their cathode point are connected together at the P terminal. Similarly, for diodes 2 and 4, their anode points are connected at the N terminal together. And for diodes 1 and 3, the cathode points are connected to different points, and vice versa for diodes 2 and 4. So we can, these are the diodes 1 and 3 are connected in what is called common cathode connection, and diodes 2 and 4 are connected in common anode connection. And how we determine which diode will turn on is based on which configuration the diodes are in. So for common cathode configuration, the diode with the highest anode potential will conduct. That means diode 1 and 3, the diode which has the highest anode potential, that diode will conduct. The other diode will be reverse biased, will turn off. For common anode configuration, the diode with the lowest cathode potential will conduct. That will be forward biased, and the other one will be reverse biased. So for example, if you are in the positive half cycle of the supply, then the anode of diode 1 has a positive voltage, while the anode of diode 3 has 0 voltage. So that is why in the positive half cycle, diode 1 will conduct, because it has a higher voltage, higher potential than the anode of diode 3. For 2 and 4 diodes, if we are again in the positive half cycle, then the point 4, the diode 4, the cathode of diode 4 is connected to the positive voltage. It is at a positive potential, while the cathode of diode 2 is at 0 potential. So because the potential of 0 is less than the positive potential, that is why diode number 2 will turn on for the positive half cycle. So this is how we determine which diode will turn on. And you can understand that, for example, if we have, let's say for example, if we have 15 volts at the anode of diode 1 and 10 volts at the anode of diode 3. So this principle says that diode 1 should conduct. But let us say, for example, to understand, let's say diode 3 conducts. Diode 3 has a 10 volts potential at its anode, and diode 1 has 15 volts. So diode 1 has higher voltage, but let us say for the sake of argument that diode 3 will conduct. Then this 10 volts will basically come to the point P. And let's say if the diode 3 has a negligible drop, then this 10 volts will come at point P. And since uh, the anode of diode 1 has 15 volts, then and the cathode now has 10 volts, diode 1 will also be forward biased. So if we say that diode 3 conducts, then diode 1 will also conduct. So the supply will basically be shorted. And because the 15 volt is higher, so current should flow in from diode 1 to diode 3. But since diode will not allow a negative current, that is why diode 3 cannot conduct. So this basically you can understand uh, the diode with the higher anode potential, that is the only one that will conduct. The others will not conduct. And you can have a similar understanding for the common anode connection as well. So this is how we determine which diode will conduct. And this is called natural conduction or commutation. Commutation means when the uh, conducting device changes from one device to another device. So if the voltage is changing and before the D1 was at higher potential and then D3 becomes at higher potential, then D3 will conduct and D1 will stop conducting. So that is commutation from 1 to 3. So this is called natural commutation. Now, uh, depending on the different types of loads that we have, the load will determine what kind of voltage we get and what kind of current we have at the output. And so we can have different kinds of loads. We can have a resistive load, an inductive load, or an RL load, a capacitive load, or an RC load. And in practice, we will not have pure loads. So we will not have a purely resistive load or a pure inductive load, pure capacitive load. We will usually have an RL load or an RC load, or we can have an RLE load, as you will see. So in an inductive load or an RL load, uh, because of the inductor current will stay can stay uh, positive or conducting for a longer period of time than if we only had a resistor. So for example, here I've shown a single phase full bridge fully controlled circuit. And as you can see, the supply voltage is Vs. And after an angle of alpha, we are giving the pulses to the thyristors. So the voltage then comes across the output. And because of the inductance, the load current is constant and ripple free. So that is reflected in the source current as well. The source current is like a square wave. So due to the presence of the inductor, if the inductor is high enough, then the load DC current will be continuous. So it will not stop. It will not die down and go to zero. And because of this inductance, it will also allow for negative load voltages. So if we only had a resistive load, then the output current will follow the polarity of the output voltage. So if we had a positive voltage, the output current would be positive, and if we had a negative voltage, the output current would be negative for a purely resistive load. But since in all the rectifier circuits that we have, the load current, the output current cannot be negative because the diodes and SCRs, they do not allow negative current. So if you see, if the current had been negative, then it would have to go in the negative direction for these top thyristors. But that is not possible. So for a resistive load, we cannot have negative voltages because that would imply negative current. But for an inductive load and an RL load, because the inductor current will always it will allow positive current even if we have a negative voltage across the full load. So that is why, due to the presence of the inductor, we can have negative voltages at the output. Like you're seeing here, the output is positive and then it goes negative. And but in this case, the average output voltage is positive. But if we change the triggering angle alpha, if we increase it beyond 90 degrees, the average output voltage itself can become negative, while the output current remains positive. So in that way, we can have a regenerative option. Uh, the power goes from DC to AC. So someone had asked in the previous session that how can thyristors allow for regeneration when they do not allow a negative current? But it is because of the negative voltage handling capability that the output voltage can become negative while the current remains positive. So that is how why we can have negative power flow, and that allows for regeneration option in the motor loads where the power flows from the motor to the source supply in case of when we are breaking the motor. So this was for RL loads. Now, if we do not want negative voltages, uh, Swarna has raised her hand. Do you have a question? Yes. Okay. Uh, so let us imagine we don't have an inductance. We only have a purely resistive load. Then, if you see this voltage, the V out voltage, which is in dark black, the current will follow this waveform. It will start here, it will be positive, and then it will become zero. And when it goes to zero, the conduction will stop, the voltage will also become zero, it will not carry on. So that is for a purely resistive load. But now if we add some inductance to it, because the inductance, uh, the inductor basically, as the current in the inductor increases, it will basically have stored magnetic energy. So when the voltage across this V out voltage becomes zero, the current is still not zero because of this inductance, and it will not uh, allow. So it will not allow the conduction to stop because the inductor cannot have sudden changes in the current. So if the inductor current is not zero while the output voltage becomes zero, the inductor will just keep the conduction going, and the output voltage will go to the negative portion. And if the inductance we are now keep on increasing, then the current will basically not the ripple in the current. So current can have a waveform like a sinusoidal waveform, but if the inductance value is very high, then the ripple in the inductor will be smaller and smaller. And for a very high inductance, we can say the load current will become almost constant. So this IS is not the load current, it is the supply current. The load current will just be this positive current for the entire duration. So that is how we can say it for if we have an inductor, then the DC current will be continuous. Okay. So if we now don't want to have a negative voltage at the output because our average output voltage is decreasing because of this negative voltage, then we can have a freewheeling diode. So this diode is connected in parallel or anti-parallel, we can say, with the load. And basically, when the output voltage becomes zero, this diode will not allow it to become negative because if it becomes negative, then the freewheeling diode will become forward biased, and basically the load voltage will then become zero. If this is forward biased, then the load is shorted. So and then the inductor current will basically flow through this uh, freewheeling diode. So that is how the inductor current will remain conducting. It will not go to zero because of this freewheeling diode, but the output voltage will remain only positive. So because of this freewheeling diode, our uh, average output voltage increases. And but since our input power is the same and our output voltage is increasing, so our output power is also increasing. So it basically improves the power factor of the circuit. So that is the advantage of having a freewheeling diode. And this freewheeling diode is only used for inductive loads because that is where the uh, current is conducting and that is where it has usefulness. So that was for inductive or RL loads. Now we can also have a capacitive load, and this capacitor is connected in parallel with some resistance or some other kind of a load. And this is a very common circuit in low power applications where we want so instead of a pulsating DC voltage, we want a stay for a relatively constant voltage at the output. That is where we use a capacitor in parallel with the whatever load we have. So in this case, the output voltage will look like this, what we have in the top. So what I have shown in the gray is basically the rectified voltage that should have been at the output of the rectifier. But because of the capacitor, the output voltage will not follow this sinusoidal pulses. So the capacitor will retain its voltage. So this voltage, for example, if I start at the peak of the voltage, the capacitor will retain the voltage and it will slowly give the current to the load, and that is how the voltage across the capacitor will slowly fall. But since the output voltage is higher than the supply voltage, these diodes will not be forward biased. Because of the supply, they will not be forward biased, so they will remain off, they will be reverse biased. But at this point, once the output voltage intersects with the rectified supply voltage, at this point, these diodes will turn on. They will be forward biased. So then, only then we will get some current from the supply, and this current will be basically it will charge the capacitor again. So these capacitor voltage will keep on charging. It will follow the supply voltage, and once it reaches the peak, it will then again store or retain the voltage, and the diodes will again be reverse biased. And the current I here, uh, it will basically be only the charging current of the capacitor. And this current will then be reflected in the source current. And as you can see, the source current will have a highly distorted waveform. So ideally, we would like to have a sinusoidal waveform at the source current. But since this current is it's a very peaky current, it's highly distorted current. So the THD of this current is going to be very high. So we will see later on in the next week how we can improve this kind of a circuit. But this is how basically the advantage of having the capacitor is basically we can get a very constant or relatively constant output voltage instead of a pulsating output voltage. But the disadvantage is the highly distorted supply current. As I've mentioned in the previous lecture, that if the THD of the supply current is high, then the voltage at the point of common coupling will be distorted also, and that can create problems for some other appliances. And finally, we can have an RLE load. So this is going to be the case for a DC motor load where we can have a back EMF of the motor. So that will come across the load. So here, for example, I've shown a half wave uncontrolled rectifier circuit. And so what the result of this having an E, which is basically the EMF, what happens because of the EMF is that the diode will not be forward biased until the supply voltage reaches or crosses the E voltage level. So before the supply reaches the E level, the diode will remain reverse biased because the voltage at this point, if this does not have any current flowing through this, then the voltage at the cathode of the diode will basically be E potential. And as long as the supply voltage is less than the E potential, the diode will remain reverse biased. And after the supply voltage crosses the E voltage, then it will turn on. So then we will get the voltage at the output. And here I have again shown a RL circuit. So here, Swarna had asked what will the current be like in the inductive load. So here you can see the inductor current basically remains, it will continue beyond even the positive voltage. It will allow the voltage to become negative. And had the inductance been higher, this current will continue even further. And had we had a full wave rectifier circuit, then we can have a uh, fully continuous current. It will not go to zero at all. And so another point that is important here is because of this E voltage, the natural commutation angle changes. So before, if we did not have this E voltage, naturally the diode will be forward biased at the when the angle was zero. But because of this E voltage, now the angle of natural commutation becomes what I've shown gamma here. So is the voltage waveform common for every type of motor load? Uh, no, it will not be common because it will also depend on the circuit. So it is not only dependent on the load, but also on the circuit. If you have a half wave circuit, full wave circuit, single phase or three phase circuit. For okay, induction. So induction motor is an AC motor. So we will not use this kind of a circuit. So this is AC to DC conversion. So we will only use it for DC motor loads. For induction motor loads, we will have a different kind of a so that we can have a AC to DC, sorry, DC to AC converter, which will be like a voltage source inverter or some other circuit. But this kind of a circuit we will not use for induction motors. But for different DC motors, uh, depending on what kind of a motor it is, so this is a uh, general load, we can say an RLD load. But if it is a series motor or a shunt motor, then the inductance value or the field inductance, that those things will change. But uh, this can be a general basically representation of a DC motor load, but not an induction motor. Okay, so I will continue now. So I will now talk about the effect of inductance. So what is source inductance? So uh, so Ajay is asking, how does the voltage source in the load act on the current and voltage waveforms? Okay, so basically what happens because of this E voltage, the level of this E voltage will determine uh, what is the current. So first of all, it will also determine the DC voltage. As I've shown, it will change, this gamma angle will change depending on the E voltage. So the average output voltage will change depending on the E voltage. And once we have the average output voltage, the average output current will basically be uh, the average output voltage divided by the resistance. Because the inductance will not show any impedance to a DC voltage, the average output voltage will basically be the average output current, sorry, will be the uh, average output voltage divided by the resistance. But because of this voltage, it will basically it will be subtracted from the average output voltage. So the average current will be V out average minus E divided by the resistance. So that is how the value of this E will change the load current. And we will see in one of the problems in detail how this will happen. But yes, it will not only change the average output voltage, it will also change the average output current. So the amplitude of this E voltage. Okay, I was saying the source inductance is basically if we have a transformer at the supply, at the input of the rectifier, that transformer will have some leakage inductance. So that will act as the source inductance. Or even if we don't have a transformer, if we have a grid connection or some generator, some AC generator, it will still have some internal impedance of that voltage source. And that internal impedance is mostly it is inductive. So in practice, you will always have an inductance connected to the source. So so let us consider a circuit without source inductance. For example, this is a full wave uh, diode bridge circuit, an uncontrolled circuit using a single phase supply. And you can see the output voltage will basically be the only the positive portions of the supply. And the supply current in an ideal case, if we have a constant current at the load, the supply current will be a square wave. So when the supply voltage is positive, diodes D1 and D2 will turn on, and the supply voltage will be positive. You see it from the supply, it will go to D1 and then back to D2. So the supply current will be positive. And during the negative half cycle, D3 and D4 will be on. So then if we see from uh, from D3, if this D3 is on and D4 is on, so that means the supply current is negative. Okay, so this is how the supply current will look like in an ideal circuit. But in a practical circuit, the source will have some inductance. And as I mentioned in the first lecture as well as the previous lecture, that because of this inductance, it will not allow an instantaneous change in the current. So here, as you can see at the 0 angle and the pi angle, 2 pi angle, we are saying that in an ideal case, the source current should suddenly go from positive to negative. But because of the practical inductance, this will not happen suddenly. So it will take some time to go from from negative to positive and some positive to negative. So in a practical circuit, that this is how the current will look like. So the IS current, when the diodes become forward biased, basically when the positive half cycle starts. So before this, D3 and D4 were conducting, and after this, D1 and D2 will have to conduct, but they will not conduct instantaneously. It will take some time for the supply current, the source current, to rise from negative to positive. And while this uh, current is rising, because our load, we are saying that the load is highly inductive, so it will have a constant current. And we are saying it is highly inductive, so this constant current will not change. So because of this, during this commutation interval, all the four diodes will be on. So they will all be carrying some portion of this load current. And because all the four diodes are on, the voltage at the output will basically be shorted. As you can see, if two and three are on, then the output voltage is shorted. And diodes 1 and 4 are on, then the output voltage is shorted. So because of this gradual rise of current, the output voltage will have this a notch kind of a waveform, and because of this, the average output voltage will reduce. So that is the effect of having the source inductance. So the source current will have a gradual rise and fall, and the output voltage will basically be reduced. The average output voltage will be reduced because of this source inductance. So based on the inductor current, inductor voltage, inductor equation, the L di dt is equal to the inductor voltage. If you use that equation, you can find out this how long will this commutation interval be, this uh, mu angle will be. So for this circuit, this cos mu will be given by the first equation. And you can see that this overlap angle will increase with the inductance. Based on this equation, the overlap angle will increase with inductance and the load current. And that is understandable because if we have a higher inductance, it will not allow the current to change suddenly. So it will further reduce the slope of this rise and fall. So that will take more time for the IS current to rise. And also, if we increase the load output current, then this interval will also rise. And that is also understandable because if it has to go from negative to a higher positive current, then it will take more time. And this the overlap angle will be reduced with if we increase the voltage, because the voltage is in the denominator here. And this will also affect the average output voltage, which is given in the second equation. Because of this uh, commutation, there comes another term which is subtracted from the the original voltage. And if this Ls is 0, then this term will basically become 0. So because of this inductance, the average output voltage is reduced. Okay, so this was the summary of the week 1. So I've not talked about multi-pulse converters, but so that is a bit complicated circuit, and I don't think you have many problems in that as well. But you can uh, study the lectures, and you can study the one of the books that was suggested is High Power Converters by Bin Wu, and in that book you can find some content related to multi-pulse converters. So now I'll carry on with the problem solving. So for this week problem solving, we will have mostly numerical questions. So obviously I cannot ask you to guess the answer or tell the answer. It will take some time. So I will just uh, mention the question and we'll start. I'll show the solutions step by step. So the first question says that we have a three-phase diode bridge rectifier and it is charging a 240-volt battery. So this is on the load we have an E. We have a voltage, a 240-volt E, and the input voltage to the rectifier is three-phase 230-volt 50 hertz. So whenever it is given 230 volts, you should understand that this 230 volts is the phase voltage. And if it was given 400 volts or 415 volts, then that would have been the line voltage. So 230 volts here we will take as the phase voltage. At current limiting series resistance in series with the battery is 8 ohms, and an inductor makes the load current almost ripple free. So here we have an RLE load, but it's not a DC motor load, it's a battery. So it has a resistance for current limiting and an inductance, and the battery itself is 240 volts. So what will be the value of current distortion factor and the input power factor? So first we'll see the circuit, how the circuit looks like. So it's a three-phase diode bridge rectifier. So we have these six diodes and three-phase supply at the input. So here I've shown the three-phase supply. So the gray voltages are the three-phase supply VAN, VBN, VCN. So these are the phase voltages. So if we apply the principle that I mentioned about the common anode and common cathode configurations, then we will see that the different diodes will be forward biased at different points. So here I've written point 1. So this is the point, this is the angle when the diode 1 becomes forward biased. Because as you can see at point P, we have three diodes connected, diode 1, 3, and 5. And whichever of these will have the highest anode voltage, that one will conduct. So since diode 1 is connected to VAN, whenever VAN is the highest among these three voltages, then at that point diode 1 will conduct. So that happens at this point. So at an angle of theta, diode 1 becomes forward biased. Similarly, at this point where I've shown is the cursor, at this point diode number 2 becomes forward biased. And this is in common anode configuration. At this point, the voltage VC is the minimum, it is the most negative. So at that point, diode 2 will become forward biased and it will start conducting. And similarly, you can see when the diode 1, 2, 3, 4, 5, 6. So that is how the numbering is being done so that they will conduct in a sequential fashion. So then you can see, for example, in this interval, when the VAN voltage is beyond 90 degrees, at that in this interval, diode 1 and diode 2 are on. So in this 60-degree interval, diode 1 and 2 are on. So then at the output, at the P point, we will get A voltage. And since diode 2 is on, at this N point, we will get VC voltage. So the total load voltage will be VA minus VC. So that will be the line voltage VAC. So that is what I've shown in the lower uh, diagram or waveforms. So in this interval from 2 to 3, since diodes D1 and D2 are on, we will get VAC at the output. So in this way, you can figure out in each interval, in each 60-degree interval, what will be the output voltage. And since the output voltage here has a 6 pulse waveform, so if you see from 0 to 2 pi, it has 6 pulses. So that is why it is called a 6 pulse converter. So this is how the voltage is develops at the output. And the E voltage should obviously be less than uh, the voltage here. And since I mentioned that the 230 volts is the phase voltage. So the line voltage, if you calculate 230 root 3, it will be 400 volts RMS. So the peak voltage of the line voltages will be around 550 or 560 volts. So that is much higher than the 240 volt battery. So that is why the battery will not basically uh, play any part in the when the diodes will conduct. So it will not change the diode conduction starting or ending portion. So now we can also see the current waveform. So we are saying that the load current is always continuous. It is a continuous DC current. So since at this point D1 turns on and A phase is connected to uh, diodes 1 and 4. So when diode 1 will conduct, the A current will be positive, and when diode 4 will conduct, the A phase current will be negative. So at this point, uh, we will get a positive A current. Then when the diode 3 starts conducting, the A phase voltage will become 0. And when diode 4 starts conducting, A phase voltage will become negative until diode 6 starts conducting. So this is how the phase current will look like. The other phase currents will just be 120-degree phase shifted from this current. So you can see the diode current here is what is called a quasi square wave. It's not a pure square wave. It has some zero current durations. So it is called a quasi square wave. And this current is actually very common in these circuits. So if you do the Fourier analysis of this kind of a current, you will get the RMS voltage of this current will be basically the output current, the DC output current. So this is the first equation is the RMS current of the A phase current, the RMS value of the A phase current, and the second equation is the from Fourier analysis the RMS of the fundamental of this current. So the fundamental of this current, so both cases you can see it depends on this theta angle. So theta angle is basically uh, half of this duration, half of the 60-degree duration. So it is 30 degrees in this case. So uh, if you put 30 degrees in this theta, you will basically get the RMS value of the A phase current is root of 2 by 3 into the load current, and the RMS of the fundamental is square root of 6 divided by pi into the load current, the average load current. So this is the RMS of the full current as well as the fundamental current. So the question had asked us to find out the displacement factor and the power factor. The displacement factor is given by this formula. It is the RMS of the fundamental divided by the total RMS of the waveform. And in this case, so if you put these two, using these two equations, if you substitute it in the displacement factor formula, you will get 0.95. And the power factor is basically displacement factor into the uh, cos phi. And in this case, if you see the fundamental is basically in phase with the voltage VAN. So it starts when the VAN voltage is zero, the fundamental of I is also zero. So the angle between the fundamental voltage and current is zero. So that is why the power factor will be the same as the displacement factor. So these are the answers to the first question. So it's not the displacement factor, it's the current distortion factor. So the current distortion factor and the input power factor are same, 0.955. So if anybody has any questions or confusion, you can ask in the chat. In the meanwhile, I'll continue with the second problem. So the second question says that we have a three-phase, three-pulse converter. So the previous converter was a six-pulse converter, but now this question is asking for a three-pulse converter. So that will be basically a half-wave circuit of a three-phase converter. So it is operated from a three-phase 230 volt 50 hertz supply. Again, this 230 volt is the phase voltage with load resistance equal to 10 ohm. Find the value of the firing angle if an average output voltage is 50% of the maximum possible output voltage required. So because it is asking about firing angle, so it has to be a controlled rectifier. And since it is only talking about a load resistance, so it is a resistive load, purely resistive load. That is what the question is asking. So this is the circuit, how the circuit will look like. It is a three-phase, half-wave, fully controlled circuit. So we have three SCRs, and the load here will be a pure resistor. It will only have an R here. So here I have shown what will be the maximum output voltage. So let's say if the firing angle was zero, the alpha angle was zero, then the output voltage will just be the positive portions of the three-phase voltages. So this is, and if you integrate, if you find the average value of this voltage, you will get the maximum voltage will be given by this formula. But now the question is asking when will, at what firing angle will we get 50% of this V max? So if we have a firing angle which is less than 30 degrees, pi by 6, then we will get a voltage waveform like this. And so this is alpha here, that is the firing angle. And if you basically find the average, you will get this equation. So it is just the maximum voltage times cosine of alpha. Now you can try to see when this voltage becomes 50% of the maximum voltage. But the problem is this, in that case, this alpha will be 60 degrees. However, for a purely resistive load, for an alpha which is greater than 30 degrees, the voltage waveform will change slightly. So for a purely resistive load, so as I mentioned previously, for a purely resistive load, since the current cannot become negative, the voltage will also, it cannot become negative. So because the voltage cannot become negative for an alpha greater than pi by 6, we will have zero voltage regions. And because of these zero voltage regions, the output voltage will, the equation for the expression for the average output voltage will change. So it will have this expression. So this is not the same expression as the previous. So for alpha greater than pi by 6, this is the expression we will get. And if you now substitute, if you want a output voltage which is 50% of the V out max, if you substitute V out as 50% of this V out max, and then you will basically cancel out the VM voltage, and you can then find out what will be the value of alpha. And in this case, it turns out the alpha value is around 67 or 67.7 degrees. So the answer to this question, so basically the point here in this question, what you had to understand is that for a purely resistive load, the current is always in all the rectifier circuits, the current cannot be negative. So because in a resistive load, the voltage waveforms follows the current waveform. Since the current cannot be negative, the voltage will also be not be negative. So the voltage for an alpha greater than pi by 6, it will have zero, zero voltage regions. So, and then you can find out the average. So the answer to this question is 67.7 degrees. So moving on to the third question. So now the third question is asking uh, for a one pulse SCR. So the first question was 6 pulse. It was basically a three-phase full bridge. The second question was a 3 pulse. So it was a half wave circuit. So in this case, it is a one pulse circuit. So it will also be half wave, but single phase also. So the question is saying that it is triggered at a firing angle of 40 degrees and the load current extinguishes at an angle of 120 degrees. So find the average load current for the resistance and inductance is given. So this is how the circuit will look like. So it's a half wave controlled single phase circuit, rectifier circuit, and we have an RL load. And the question is saying, so at an angle of alpha, we are triggering the output voltage and at some angle beta, the output current basically becomes extinguished. So since the output current becomes zero, the output voltage will also become zero because the uh, output voltage cannot continue if the current is zero because the thyristor will simply stop conducting. So we are asked what is the average current. So if we want to find the average current, we can find the average voltage and then we just have to divide by the resistance because the inductor will not have any impedance to a DC load. You can understand the impedance of the inductor is basically omega L. Omega is the frequency of the voltage supply. But since in a DC average sense, the frequency of the DC is zero, so the impedance of the inductor is also zero. So we will only have the impedance of the resistor. So you can find out if you integrate this voltage, you can find out the average output voltage. It will be given by this expression. And if you substitute alpha as 40 degree and beta as 120 degree, then you will get an output voltage, average output voltage of 65.5 volts. And then using this average output voltage and the resistance which is given in the question, you will find out that the average current is 13.1 amperes. So the answer to this question is 13.1 amperes. So that was the third question. So the fourth question is asking which of the following option denoted the advantage of freewheeling diode in a rectifier circuit. And the options are input power factor is improved, load current waveform is improved, input power factor and load current waveform both are improved, or and the fourth option is either of these two is improved. So here you can, Nirasa, you have your hand raised. You have a question. Nirasa, do you have a question? Okay, I will just carry on. So some of you have uh, guessed the right answer. So basically, because of the freewheeling diode, as I mentioned, the output voltage uh, does not become negative. So the average output voltage increases. And since the average output voltage increases, the power factor will improve. And because of the freewheeling diode, when the voltage becomes zero, so the, the inductor current will then, Nirasa, your mic is on. Do you have a question? Yeah. Yes. Sorry, I'm not able to hear you clearly. Yes, full wave and half wave. Uh, Okay, you want to know the difference between full wave and half wave rectifier. The half wave rectifier circuit is like this. It basically has only one diode or one SCR. So it will only conduct during the positive half cycle of the voltage. So that is why it is called a half wave rectifier. A full wave will be the current. Uh, yeah, the current will increase during the positive portion, and then if it is an RL load, it will continue and then it will extinguish at some point. Okay, okay, you can mute yourself. Okay, as I was saying that because of this freewheeling diode, the output average output voltage will improve, so the power factor will improve, and the current will also the output current will also improve because this diode will provide a path for the a low resistance path for the current to continue. So in that way, the inductor current can continue for a longer duration. So the answer to this problem is that the input power factor as well as the load current waveform both are improved because of the uh, freewheeling diode rectifier circuit. So the fifth question is asking a one pulse SCR. So again, that is it's a half wave circuit is triggered at an angle of alpha and the load current extinguishes at an angle of beta. What will be the circuit off turn off time if the load is considered an RL type load? Okay, someone has actually uh, given the so let's see whether this answer is correct or not. So this is the circuit how so it is similar to the one of the previous problems. So we have a single phase one it's a one pulse, so that is why it's a half wave circuit. So we only have one SCR and then we have an RL load. So after the firing angle, the current will start conducting and the output will voltage will become positive, and then the when the current the voltage drops, the current will also drop, and at some point the current will become zero, and that using an inductive load it will happen after the pi point. And so basically after this pi region somewhere the output current will become zero. And so the turn on time is basically whenever the output current is positive. So if you see the turn on time is from the turn on angle is from beta minus alpha, and the turn off time will basically be all the rest of the time. Okay, so omega t on is beta minus alpha. So omega t, so this scale, the x-axis is omega t. So omega t is zero because an actual time scale will be in, it will not be in radians, it will be in seconds. But omega time scale, omega t scale would be in radians. So omega t when the turn on time is omega t equal to beta minus alpha. So this duration when the uh, load current is positive, this is the turn on time. The off time will be the rest of the duration, which is 2 pi minus the on time. So 2 pi minus beta minus alpha. So then the if you do basically find out T off, you will get 2 pi plus alpha minus beta divided by omega. So that is the turn off time of this circuit. So the answer B is correct. Okay, so it is 2 pi plus alpha minus beta. So this was the fifth problem. So before continuing, we can have a short break right now. So then we can continue at 7:10 p.m. So for 5 minutes, we'll have a break. So in the meantime, so those who are interested, they can see the sixth problem. They can try to solve it. Okay, so we can have a short break right now. Okay, let's continue. So the sixth problem says that we have a three-phase full converter. So a full converter basically means a fully controlled converter which has six SCRs. It is connected to a supply voltage of 230 volt per phase and a frequency of 50 hertz. The source inductance is 4 millihenry. So this is a question with the source inductance as well. So we will have an overlap angle where the source current rises or falls. The load side current, DC current, is constant at 20 amperes. If the load consists of a DC source of internal EMF 400 volts with internal resistance of 1 ohm, then what will be the value of overlap angle in degrees? So this is the converter, how the converter looks like. And so I've only shown the resistance and the EMF voltage of the load. But since it's a constant current, you will also have some kind of an inductance. But so these circuit and waveforms are without source inductance. So let's see first how the circuit will look like, how the waveforms will look like without the source inductance. So the I have shown here at 1, 2, 3, all these are the points of natural commutation. So these are the points where the SCR would have been forward biased if it had been given a continuous gate current. So at point 1, the SCR1, the thyristor 1, uh, has the most forward positive voltage at the anode. But since we have not given the gate current yet, so that is why it will not turn on at 1. It will turn on after the angle alpha. So this alpha is basically from the natural commutation instant. So this instant at the where I've written 1. So this is the natural commutation instant. And after an angle of alpha, we are turning on the thyristor 1. So then the voltage at the output basically, so the output voltage is basically some phase voltage minus another phase voltage. So if you see the depending on the alpha angle, the output voltage will be, let's say in this period, it will be VAN minus VBN because this voltage is VBN. So then we will get VAB in this portion. And similarly, we can continue depending on the alpha angle, the voltage will look like this. And so this is for an alpha angle less than, let's say, 60 degrees. So if we keep on increasing this alpha angle, the output voltage, the average output voltage will become zero, and then it can also go negative if we have an inductance or a load which can have a constant current. So this was the voltage waveforms. Now, how does the current look like? So the supply current will basically turn on whenever the thyristor 1 is on. The supply current through phase A, the phase A current will be positive, and when thyristor 4 is on, the phase A current will be negative. So if you see based on the voltage, this is how the current will look like. And the angle between the voltage waveform and the current waveform is alpha. So for if it had been diodes only, this angle would have been zero. So the fundamental of the phase current would have been in phase with the fundamental or the supply voltage. But because we have thyristors and because of this triggering angle, this alpha is basically reflected in the fundamental of the load current. Now this was how the circuit will behave for a if it had no source inductance. Then the current will rise suddenly, as I've shown here for A phase current. The current rises and falls suddenly. However, now if we have a source inductance, then the current will rise and fall gradually, and there will be some duration during which the current is rising. And in that duration, multiple thyristors will turn on. So, for example, here, uh, before this instant, before the alpha instant, here uh, in the top, among the top thyristors, thyristor 5 was on because we had turned on 5 at this point. So 5 was on. And now we are turning on thyristor 1. So because of the source inductance, the thyristor 5 and 1 will be simultaneously be on for some time. And during that time, the source current will rise. And because of two uh, two diodes be coming on at the same time, so the output voltage will reduce. So there will be a notch in the output voltage. So this will happen. This is what will happen in case of source inductance. Because of the source inductance, the output voltage will have a notch. It will the output voltage average output voltage will reduce, and the source current will rise gradually. Now the question is asking basically what will be this overlap angle. The angle mu is called the overlap angle because at this point, during this interval, multiple currents are flowing. Basically, multiple diodes are on, so they are overlapping. The currents are overlapping. So if we see that the average output voltage, so we are given that the uh, internal EMF is 400 volts, the current is 20 amperes, and the resistance is 1 ohm. So we can find out the average output voltage would be 420 volts. Then using this equation, the equation for the three-phase circuit with the source inductance, you can find out uh, in the course lectures or in the textbooks. You can find out what will be the average output voltage, and it will be basically dependent on the line-to-line voltage and the alpha angle, the source inductance, and the load current. So in this equation, we have already determined what is the load voltage. We know what is the line to line voltage. So I think it is 230 volts. So the line to line voltage will be 230 root 3. We know the inductance omega is 2 pi f. F is 50 hertz. And the output current is 20 amperes. So in this equation, we know all the values except for alpha. So if we substitute all the values, we can find out alpha, which will be turn out to be 34.38 degrees. And then we can have another equation from the volt second balance of this source inductance. Then you will get the second equation where the cosine of alpha plus mu, the overlap angle, is cosine of alpha minus this second term. And once we have found out alpha in this equation, only thing that is unknown is the mu angle, which we have to find out. So if you substitute all the other values, then you can find out that the mu value becomes 8.22 degrees. So the overlap angle is 8 degrees. So you can understand that the overlap angle is not too much. So here I have shown it as an exaggerated view just to make it clear. But in practice, because the source inductance is quite low, the current will rise relatively fast. It will only take 8 degrees. So you can find out that 8 out of 360 is a very small fraction of the total time duration. So the answer to this problem is 8.22 degrees. So the next problem says that a single phase fully controlled thyristor bridge AC-DC converter is operating at a firing angle of 35 degrees and an overlap angle of 50 degree and a constant DC output current of 20 amperes. So we have a fully controlled thyristor bridge. So we have four thyristors and a single phase supply. So firing angle is given and an overlap angle is given. So if you are given an overlap angle, you understand that there is a source inductance. And the DC output current is also given. Yes, Vishal, you have a question? Uh, so if you go to the course website, So at the end, you will have some uh, problem solving session recording or something like that. So they will that will send you to a Excel sheet, and in that Excel sheet you will find this video lectures as well as the slides. There are a Google Drive folder for these slides. And so if you cannot find it, you can search on YouTube NPTEL sessions with Saleh Khan, Saleh. Okay, I will write in the chat. Okay, so if you search on YouTube NPTEL sessions with Saleh Khan, you will find the YouTube channel where all these lectures are uploaded, and I will include the slides in the description of those videos. Okay. Okay, so as I was saying that in this question we are given an overlap angle. So if you're given an overlap angle, you must understand that uh, this question has a source inductance also included. Then the question is also asking about the fundamental power factor at the input. So the fundamental power factor is basically the cosine of the angle between the fundamental supply voltage and the fundamental supply current. So you know that the supply current here will be some kind of a square wave or a quasi square wave, but it will have a uh, fundamental of that current. The angle between the fundamental current as and the fundamental voltage, the cosine of that angle is the fundamental power factor. So this is the circuit. It is a single phase circuit, fully controlled SCR bridge with a source inductance and a constant output current. And as you can see that because of this alpha angle, the current will be delayed, and because of the source inductance, the current will rise slowly. So it will have a overlap angle mu. So you are given this uh, alpha angle as well as mu angle. So you can understand just by looking at it that the fundamental of the current will pass through this point where the actual current goes through zero. So this is how the fundamental will look like. I've shown it in dashed gray. And then you can see because this mu current is mu angle is it is symmetric basically in the positive half cycle and the negative half cycle of the current. So the current will cross zero when at an angle of alpha plus mu by 2. So half of the mu angle, that is where the current will cross. So the fundamental power factor will be the angle will be alpha plus mu divided by 2, the half of this mu angle. So the fundamental power factor will be cosine of that angle. And since the angles are given, the alpha is 35 degrees and mu is 15 degrees, then you can substitute in this equation and you can find out that the fundamental power factor is 0.737. So the answer to this question is A, 0.737. So next question says that we have a three-phase full converter. So three-phase full converter means you have a three-phase supply and six SCRs, so six thyristors. It delivers a ripple-free load current. So again, it will have some kind of an inductive load which will give a continuous 10 ampere current with a firing angle delay of 50 degrees. So the alpha angle is also given. The input voltage is 400 volts 50 hertz. What will be the value of active input power and reactive input power? So this is the circuit and these are the waveforms, the voltage and current waveforms. So after an angle of alpha, the thyristor 1 is on. So the current will, the A phase current will basically turn on at this point when the thyristor 1 turns on. And it will conduct for 120 degrees and after that it will stop for 60 degrees. And then when the thyristor 4 is turned on, then the A phase current will be in the negative. And the angle between the fundamental of the voltage and the fundamental of current, if you see, it will be this alpha angle. So because this duration is 60 degrees, so you can just see that the alpha angle will, the power factor between the voltage and current will be this alpha angle. So had there been and source inductance also, then there would have been alpha plus mu by 2. But this question is not asking about any source inductance, so the power factor angle is alpha. So now the question is asking about the active and reactive powers. So because we know, as I mentioned, it's a quasi square wave current, and you can find out the fundamental RMS of the fundamental of the quasi square wave current. It will be given by this equation, the first equation, which is the A phase fundamental RMS, and it is given by this expression, and the cosine of in this case it will be the 60-degree portion where the current is 0 divided by 2. So it is actually from the 0 crossing to where the quasi square wave turns on. So this angle is 60 degree divided by 2, and if you see, then it will get a current of root 6 by pi into the output current. And as I mentioned, the angle between the fundamentals of voltage and current is alpha. So based on this, we can now find out what will be the power, active power. The active power will be 3 times the phase voltage. So we are given the line voltage. So divided that by root 3, you will get the phase voltage. The fundamental current you can get from the first expression using the Fourier analysis of this quasi square wave. So that you can get, and the cosine of phi 1, and phi 1 in this case is alpha. So all of these you know, because you are given the supply voltage, you are given the load current, you are given the firing angle. So if you substitute all these values, you will get a active power of 3.47 kilowatt. And similarly, just instead of cosine, if you have a sine, you can get the reactive power also. It will be 4.13 or 1314 kilowatt. So this is the answer to this question. The answer is C. So now the ninth question is asking about a 12 pulse converter. So the question is 12 pulse converter with a resistive load, what will be the maximum possible firing angle? So does anybody know the answer to this question? Or can anybody guess what should be the answer? Okay, some people are saying 60 degrees. One person is saying 120 degrees. But okay, let me go back to understand this question. So uh, just a minute. Okay, so let me go back to this question. So this circuit was it was a 3-pulse circuit. In a 3-pulse circuit with a resistive load. So the resistive load portion is important. Uh, the resistive load means that the voltage cannot become negative. And since the voltage cannot become negative, the alpha angle is limited. So in this case, you can see, because the voltage cannot go negative, the alpha angle, if I keep on increasing to more than this point, then we will not get any voltage at the output. So the alpha angle cannot go. So in this case, this is basically a 3-pulse converter. The alpha angle, which starts from this line, it can go at maximum to this portion, which is the omega t is equal to pi. So the maximum alpha angle will be pi minus 30 degree or 150 degrees. So it is because of the resistive load. Had it been an inductive load or an RL load or RLE load, then we could have increased alpha beyond this portion because the voltage would have been negative. It would have been continued to give some output voltage. But because it is a resistive load, the voltage cannot become negative. So alpha angle we can, for a 3 pulse converter, the maximum alpha angle can be 150 degrees. So now the question is asking about a 12 pulse converter. So before 12 pulse, we can see what will happen for a 6 pulse case. So this is the 6 pulse case. The alpha starts this from the left line. And as you can see, again, because of a resistive load, the voltage, we cannot have a negative voltage. So the alpha max for a 6 pulse case can be maximum of 120 degrees, because after 120 degrees, the output voltage will just become zero. So because the output voltage right now is like this, but had the angle been higher, then the output voltage would have been from here to somewhere here, and then it will go on. And had the output voltage been very high, sorry, the alpha angle would be very high, then the output voltage will go to this region and then will remain zero, and then it will go to the next voltage. But for an alpha angle beyond 120 degree, we will not get any output voltage, because the this, you can see the voltage in the red, it goes to negative. Beyond alpha max equal to 120 degree, the red voltage goes to negative portion, and because of the resistive load, we can not have the negative voltage. So this was for a 6 pulse converter. Now for a 12 pulse converter, you can understand, based on the how many pulses there are, you can see that the alpha max can be a maximum of 405 degrees. So you can just uh, later on you can see how these, because all these portions are 60 degrees. So this is a 60-degree portion, this is another 60-degree portion. Sorry, these are 30 degrees portion. So this is a 12 pulse is a 30-degree portion. So these are 30 degrees, another 30 degrees, another 30 degrees. So these three become 90 degrees. And then we have half of this portion, which is another 15 degrees. So the total angle is 105 degrees. So for a 12 pulse converter with a resistive load, the maximum alpha angle, triggering angle, can be 105 degrees, because beyond this angle, you will not get any voltage. You will get a zero voltage. So the answer to this question is 105 degrees, the D option. Okay, so now we can move on to the final question, which is a single phase full converter feeds power to an RLD load with the resistance is 5 ohm, the inductance is 6 millihenry, and the voltage of E is 50 volts. The AC source is 230 volts. So this is a single phase source, so it's a 230 volt, 50 hertz. For continuous conduction, find the average value of the load current for a firing angle delay of 45 degrees. So we are given the firing angle delay, and we know the circuit. Using the circuit, we can find out the average output voltage. And then average output voltage minus this E voltage divided by resistance will give us the average load current. But so what is important to understand here is that whether this E voltage will have any effect on the conduction. But because this E voltage is quite low, if you see, it is only 50 volts, while the AC source voltage is 230 volts. So for a 230 volt source voltage, the peak will go around 325 volts or something. So the E voltage is quite low. So, and the angle that is given, alpha angle, is 45 degrees. So it is well beyond this E voltage. So this E voltage will not have any effect on the firing angle. And the output voltage will look like this. And then you can find out what will be the average output voltage. And given the firing angle, you can get the value of average output voltage. So it will be 2 Vm by pi into cos alpha, and alpha is given as 45 degrees. So we can find out what is VO, the average output voltage. And then to get the average load current, it will just be V output average minus E divided by R. Because again, the inductor will not have any impedance to the DC portion. So the Average output current is thus given by 19.28 amperes. So the answer to this question is A, 19.28. So this concludes all the problems that we had. So if you have any questions regarding any of the problems or any of the concepts, then you're welcome to ask. Somebody wants to ask a question. Can you speak louder? You're not audible. Okay, so RLE load is basically, it depends on what kind of a load it is. So an RLE load will happen in two cases that we have seen. One is a DC motor load. In a DC motor load, because of the back EMF, you will have some voltage, and that is the E voltage. Similarly, for a battery charging application, where the battery is the E voltage. So that is, in these two cases, we can have an RLE load. The R will just be the resistance of the winding or the resistance of the wire or a current limiting resistor. The inductance will be again the inductance of the winding or the field widening in case of a motor, or it can be just the inductance of a wire, which is a very small inductance, but still it will have some value. And so these are the cases where we have RLE loads. In practice, we will not have an RLC load, okay, because RLC loads are very, in practice, I mean, you can see that you can consider the battery is also as a capacitive voltage, but in practice, RLC loads are rare. You can have an RC load where the C is in parallel with the resistance, but RLC loads are very rare. You will mostly encounter RL loads or RLE loads or RC loads where the R and C are in parallel. So someone is asking for question 7. Okay, so the active power. So in this case, basically the overlap angle, basically since it increases the power factor angle, so it will also, uh, so that means the power factor decreases, the overall power factor decreases because the angle increases. So you can understand that the active power also decreases because the active power now has this mu by 2 angle. So that is one area where it affects the active power. And also because the output voltage will also have a reduction because there will be a notch in the output voltage. So the average output voltage will also reduce. And since the average output voltage reduces, the output current also reduces. So it will have an effect on the amplitude of this supply current as well. So it will have an effect on the power factor angle. It will also have an effect on the supply current amplitude. So that means it will have an effect on the fundamental of the supply current. So in both cases, it will reduce the active power. If all other things are same, if the load resistances are same, if we just having a source inductance, the the power factor the power factor will reduce, the angle will increase, the power factor will reduce, and the uh, source source current amplitude will also reduce. So the active power overall will reduce. However, there will be one advantage: the THD will improve. So if you see the multi-phase in the lectures, the multi-pulse converter, in there you will see that the THD will improve because you can understand the having an inductance at a load, it will the change in the current will be gradual. So that means the THD will improve. Because of the sudden changes in the current or a peak having a peaky current, that is where we have a low THD. And including an inductance, it will basically filter out some current. It will act as a filter and it will improve the THD. So any other questions? Anubhav, you have any other? The freewheeling diode, so it will basically have an indirect impact because the freewheeling diode will improve the or increase the average output voltage. In this case, because we have a firing angle, the freewheeling diode will not allow the negative voltage. So in this case, there will be some negative voltage. The freewheeling diode will not allow that, so the overall output voltage will increase. So in that case, if other things are also constant, uh, the source current will also increase. So then you can find out the power factor if it is so that may improve because the power factor is has a expression of not only depends on the angle but it also depends on the fundamental divided by the total RMS. And in that case, that current may increase. So the power factor it may improve. Okay. Yes. So a chopper is usually we we consider a DC-DC buck converter is usually called a chopper. So in that case, there is only one frequency. It is the switching frequency because there is the supply's input side is DC, the output side will also be a DC. But in if somehow there is if you're using chopper for some other case, but still at 2 kilohertz frequency if it is given, then it can only be a switching frequency because the supply can only have a 50 kilohertz or a 50 hertz or a 60 hertz frequency. That is the common supply frequencies. So if it is given at 2 kilohertz frequency, then it has to be the switching frequency of the devices. But most, so if I understand that if it is given a chopper has a switching frequency, then it will be a DC-DC converter, a DC-DC buck converter, and it will be the switching frequency of the buck converter switches. Yes, so that will be the switching frequency of the MOSFET. So buck converter circuit, it will basically has an input DC voltage. Then we have a MOSFET and an inductor and the load. And between the MOSFET and inductor, it's connected a freewheeling diode. And if the switching frequency is given, then that will be the switching frequency of the MOSFET. So I think probably we'll study choppers in future classes. Uh, but basically, what I'm saying is that the switching frequency will be the switching frequency of the MOSFET. Okay. So anybody else has any questions? Reference book. Okay. So actually, I think in the first lecture of the course, uh, at the end, it was Professor Vipatacharya had told it as one of the books. So it is High Power Converters. So I'm typing High Power Converters by Bin Wu, Binwu. So that is the reference book for the multipulse converters. And for other circuits, so these circuits are very good, nicely mentioned in the Ned Mohan's book, Power Electronics by Ned Mohan. So that is also one of the reference book in the course. So if you see that the effect of the source inductance is very well explained in that book, Power Electronics by Ned Mohan. So it's a very standard book. It has had many editions and it is widely used. Okay, so any other questions or clarifications? Okay. Okay, so if there are no more questions, then who don't have any questions, they can leave. Uh, I'll stay here for a while, so if anybody has any questions they're typing or they're thinking about, they can. So, okay, so Ajay is asking what is the effect of voltage source in RLE load to the source? So as I mentioned previously, because of the RLE load, the load current will reduce. Because let's say, yeah, for example here, so if we have an RLE load, the load current will now be given by the output voltage minus this E voltage, and so the load current will reduce. And since this load current is reflected in the source, so the square wave or the quasi square wave, the amplitude of that square wave or quasi square wave is this IO. So because of this E voltage, the IO voltage, IO current, the source current amplitude will also reduce. So that is the effect. And also uh, because of the E voltage, so it can have an effect. The output voltage itself can also reduce. If the output voltage reduces, then so here the output voltage will also reduce. So the current will further reduce. So, but overall, it will just change the source current because the source voltage, of course, cannot. We are considering the source voltage to be a stiff voltage, a grid voltage, which we cannot change. We can only change the source current. So by changing the loads from RL to RLE to RC, this only the source current will change. So due to the presence of this E voltage, the source current can reduce. Okay. Okay. So anybody has any other questions, they can ask. I will be here for a few minutes. Newton Raja, do you have a question? What do you need explanation? Can you the first few slides? So uh, I was just summarizing what was taught in the week. So there was single phase, the different types of rectifier circuits. So for example, these are the half wave rectifier circuits. You can have uncontrolled on the left with only a diode and controlled on the right. So these are called half wave because they only have the positive. They will conduct during the positive voltage, and the negative voltage they cannot conduct. So they will have be half wave. Then we can have different types like so now based on full wave we can have one option is for a split phase supply where we have a center tap transformer and two supplies at the secondary, and they are connected in a certain way so that we get full wave at the output. But since this uh, having this center tap transformer is not common, so that is why this circuit is not usually used. So usually we go for full bridge rectifiers, and here we can have three options. We can have a fully uncontrolled where we can have four diodes, or we can have fully controlled where we can have four SCRs. In between, we have a few options for half controlled or what is called a semi converter. And we can have two thyristors and two diodes. So here I've shown two thyristors on the top and two diodes on the bottom. But there can be other options as well where two thyristors in one leg and two diodes in another leg, or two thyristors in diagonal, and so on. So these are the single phase rectifiers. Now coming to three phase, again we can have a half wave circuit where we only have the positive direction, and we can have, so these will be three pulse voltages, or we can have full wave where we can have six pulse voltages at the output. So again we can have fully uncontrolled, fully controlled, or in the middle we can have some kind of a half control. So these are the types of rectifiers. Next, did you listen to this portion for natural conduction commutation? Okay, so this is in many cases you will have multiple diodes or thyristors connected to a single point. For example, diode 1 and 3 are connected to the P point, and 4 and 2 are connected to the N point. So the question is, how do we determine which diode will conduct? So we can redraw this circuit in this way. And as you can see, diodes 1 and 3 are connected in what is called common cathode connection. So their cathodes are connected to the common point, and their anodes are connected to a different point. Diodes 2 and 4 are connected to a common anode connection, which is N. So their anodes are connected to the common point, while cathodes are connected to different points. So in this case, what is the principle is that in common cathode connection, the diode with the highest anode potential will conduct. So if the diode 1 has the higher anode potential compared to diode 3, then diode 1 will conduct and 3 will remain reverse biased. And for anode connection configuration, the diode with the lowest cathode potential will conduct. So if 4 is at lower potential compared to 2, then 4 will conduct. So that is why in the positive half cycle, because the positive point is higher than the negative point, then 1 will conduct and 2 will conduct, because in case 2 is connected to the lower point. Similarly, you can understand for the negative portion. So the principle is basically you will see for the common cathode connection which diode has the highest potential at the anode. And for the common anode configuration, you will see which diode has the lowest cathode potential. So that is called natural commutation or conduction. And for thyristors, this will be the portion where the alpha angle will start. The point where one or one diode has the highest potential, at that point will the thyristor angle will start. We can start alpha angle from that point. So then I talked about the different types of loads. We can have resistive loads are actually in practice uncommon. We will only have RL loads or RC loads or RLE loads. But a purely resistive load or a purely inductive load or a pure capacitive loads, these are uh, not found in practical cases. So an inductive load will have uh, the current will remain constant if the inductance is high, and because of that the voltage can go negative, because in all the circuits that we have seen, the current can only be the load current can only be positive, because the diodes and thyristors, they will not allow a negative current, but the voltage can be negative. If we have a load inductor RL load, then the load voltage can become negative because of the presence of this inductor. So the inductive load basically it allows for negative voltages, and therefore we can overall the average output voltage itself can become negative. Okay, so do you have a question? Yes. Okay, so I am okay. Let me explain. So I am talking about the DC output load. So the this R and L load, the output voltage across this load will be basically the top point and the voltage at the top point and the bottom point. And the current will be the from positive to negative. So that is the positive direction of the current. If a current is flowing from top to bottom, then we will say the current is positive. If the current is flowing from bottom to top, then the current will be negative. But in this case, you can see if the current is flowing from bottom to top, then it has to go uh, through some of the thyristors. But the thyristor will not allow a negative current. The thyristor will not allow a current from cathode to anode. So that is why for all these circuits that we have seen, we cannot have a negative load current. The DC, the load current can only go from top to bottom. It cannot be from bottom to top. But the voltage at the output, so the voltage at the between the top point and the bottom point, so that like here I've shown the V out voltage. So this voltage can become negative. So like here, this voltage is positive, and then after pi angle, it becomes negative. So this voltage can become negative, but the current remains positive. And in this case, if you find the average output voltage will also have some positive value. But if we increase the alpha angle, it can happen after alpha angle of 90 degrees that the average output voltage itself becomes negative, while the current remains positive. So the overall power becomes negative. So that is what we call regeneration. So is that clear what I'm talking about, the positive voltage, positive current? Okay. So I think the best way you have to study from the book. You have to uh, then you have to try out different circuits. You have to say, okay, let us imagine a circuit like this. So what should be the voltage and current? So that will you can have like an exercise. How what do you think the voltage and current will look like? And then to confirm your analysis, you can simulate the circuit. So there are a lot of options for simulation. You can simulate in MATLAB, Simulink, or you can simulate in LT Spice. So that is a free software. So you can include some thyristors, some diodes there, resistors, inductors, voltage sources. I mean, you will have to learn how to operate that LT-Spice or MATLAB or Simulink. That you can search on YouTube how to make a rectifier circuit on MATLAB or LT-Spice. It will take some time, but you can then try out different circuits and then you can see how the voltages and currents will look like. So that will confirm your analysis. So if you are making a mistake, that will confirm and you will be able to see the different voltages and currents in all the components. So that you can do. Okay. So I think that's it. So if you have any more questions, you can ask in the next uh, session. We'll conclude for now. Thank you for joining.